Hello, everyone. Let's continue where we finished the other day. So we were studying a partial differential equation, which is actually a model of a wider range of equations. So if you remember, we were dealing with an equation of this form. We are looking for some space, some rod or something like that. We have some x-axis. It starts at x equals 0, goes to x equals a. And then we also have, so that's one parameter, and then we have another parameter time t. And then we have a function which depends on the point x. It depends at what point x we are and what time t it is. It's like looking at temperature of a bar or something like that. If we show this quantity with u, which is a function of x and t, we are interested in finding solutions to this equation. The second derivative of u with respect to x equals a constant, which, well, the convention of the book is to use 1 over k, derivative of u with respect to t. This is the equation. We had some conditions, which they are called the boundary value conditions. So we have boundary value conditions. We want our solution, the solution we find for this equation, we want this solution to satisfy some properties. One is that if x is equal to 0, at any time t, this u of 0 and t, we want this to be equal to a constant, say t naught. And we want at the end point where x is equal to a, this function u at the point a at any time t would be equal to another constant. Let's call this t1. We had an extra condition, which we call that initial condition. It tells us this function u at any point x when t is 0. At the starting point, it tells us what is the value of this function. So if we fix t to be 0, u would be just a function of x. And suppose this function u of x and 0 is given. So I would write here f of x. It means this thing is given. This f of x is something given. It's not unknown. We know, for example, let's say it's cosine of x. Okay, it's something like that. It's something fixed and given. It's not unknown. The unknown here is u. So we are trying to solve this equation, and we want to find u at any time x and t. That is the question. Okay, is there any question here about the setting of our problem? Is it clear for everyone? Okay, great. Now, the first step usually in solving these problems, at least our approach, is what we call steady state. What do we mean by that? It's like, for example, if we have a little rod here, if in beginning each point of this rod has different temperature, if you wait long enough, you expect it would get to some steady situation, right? You think it would get to some equilibrium, right? So that's kind of the case. If a lot of time passes, so mathematically it means if t goes to infinity, we expect this function u at each point kind of becomes constant, right? After a very long time, we expect, for example, if it's temperature, the temperature wouldn't change anymore. So in other words, if t goes to infinity, we think the value of u, if we look at its derivative with respect to t, changes in the value of u with respect to time, that becomes 0. So as time goes, this function u converges to something steady state situation or steady state distribution. That is kind of an assumption, okay? We kind of assume that this should happen. We have not proved that, but that kind of makes sense, okay? So if that's the case, if when t goes to infinity, the changes in the function u with respect to time become 0, it means as we change, if we wait long enough, so infinity here, well, maybe you shouldn't really think about it as really infinity. Think about t going to infinity as a long time has passed, right? And now this condition here tells us as time passes now, u doesn't change anymore. In other words, when t goes to infinity, u does not depend on t anymore. So if you look at this function u, which a priori is a function of x and t, if t goes to infinity, this function doesn't depend on t anymore. This would be, if we assume it's convergent, it would be a function which only depends on x. We show that with v of x. So this is what we call steady state function or distribution. Okay. Now, we can look at the equations we had earlier. We were assuming that what were the equations we had? We had the derivative of u, the second derivative of u with respect to time, with respect to x, is equal to a constant. We were showing that constant is 1 over k times derivative of u with respect to t. That was one condition, right? Now, if we take limit from this equation, so if we take limits, and if we send t to infinity, what would happen? What's going to happen here? So the question is that what do we get if we take limit and send t to the equation? Send t to infinity. The equation we are going to get here is called the steady state equation. Let's find out what that equation is. Okay, so I'm going to write that equation. So we have the limit of the second derivative of u with respect to x as t goes to infinity is equal to limit of 1 over k derivative of u with respect to t as t goes to infinity, right? Now, when we have this definition, remember what v of x was. V of x, it was defined by the limit of u of x and t when t goes to infinity. Now the point is that here I can take derivative with respect to x from both sides. So when I have this, I can take partial derivative with respect to x from both sides of the equation. So I can see derivative of this function v with respect to x is equal to derivative with respect to x of this limit. So it is correct that it's not true that always derivative of limits, they commute, they interchange, but here we assume that we are in a good case. The function u is kind of well behaved. The functions where limit and derivative, they don't commute, there are some very specific, strange, not specific, there are some not well behaved functions. Suppose here we have this condition. Suppose this is equal to the limit of derivative with respect to x of u, where t goes to infinity. T goes to infinity here in both cases. And the same thing applies again. If I take the second derivative with respect to x, I can see the second derivative with respect to u is equal to the second derivative of v with respect to x is equal to the limit of second derivative of u with respect to x. Okay, so that simply means this equation here, let's call that star. It means star applies, we can take limit, and on the left-hand side, we would have the second derivative of v with respect to x is equal to, well, 1 over k is a constant, that doesn't matter. But what is the limit of derivative of u with respect to t? Well, we assume that is converging to 0. So it would be 1 over k times 0, which is 0. So in other words, the second derivative of v with respect to x is equal to 0. That is going to be our steady state equation. That's the equation we are going to get for another function v, right? Note that v is just a function of x, which its second derivative with respect to x is equal to 0. Okay, so that's one thing. What are the other assumptions we had? So we had the second derivative of u with respect to x is equal to a constant times derivative of u with respect to t. This one becomes the second derivative of v with respect to x is 0. Great. That's our equation. Now we had some boundary value conditions, right? So one of them was telling us that u at the point 0 and t is equal to t naught. Okay, now I want to see what would be the corresponding condition for v. So let's take limit from both sides and send t to infinity. So we would have limit of u of 0 and t, where t goes to infinity, is equal to the limit of this constant t naught as t goes to infinity. Now, by definition, the left-hand side, the limit of u at any point x and t when t goes to infinity is v of that point, and just v of that point. So in this case, it would be just v of 0, right? The right-hand side is a constant. The limit doesn't have any effect. So the boundary value condition becomes just v of 0 is equal to t naught. The other boundary value condition is completely similar. We would see v of a, the other endpoint, is equal to t1, the other constant number, right? Now we had another condition that was the initial condition. The initial condition was this one. We knew that u at any point x at time 0 is given by a function f of x, right? That's the initial initial condition. What happens here? Does this condition tell us anything about v? Does it have any meaning here for us or not? So the point here is that no, it really doesn't, right? Because, well, if you take limit, there is no t here, first of all. Taking limit doesn't have any meaning. On the other hand, when we are taking limit, we are thinking about the time where t is going to infinity, right? And this is the case described at the moment 0. So in some sense, it shows us that v is independent of f of x. You see, if you take limit from this equation and send t to infinity, nothing happens. There's no t here. So it tells us what happens at infinity, at the time infinity, which is described by v, is independent of the situation which we start with, which is f of x. So v kind of tells us what's going on when t is going to infinity. F tells us what's going on when t is equal to 0. And we can see f of x, it does not appear as a condition for v. So it really doesn't matter what is the situation which we start with. That does not affect v. Great. Okay. Any question up to this point? Okay. Now let's try to solve this new equation we have for v. So this is our equation for the function v, and these are our boundary value assumption for v, and there is no initial condition for v. We still have boundary value conditions, but no initial condition. This one is easy to solve. So this is our equation, and these are our boundary value conditions. Sorry, T0 and T1. Now, this is easy to solve. We would solve that now. But as you can see, the idea of using this steady state thing, this taking limit, is useful because, as you know, we started with a PDE in the sense that we had derivative with respect to x, the second derivative actually with respect to x. We also had derivative with respect to t. Now, by taking limit, we kind of got rid of one of these derivatives. We only now have the second derivative with respect to x. So there is no derivative with respect to t anymore. So we are dealing with an ODE. So rather than having different derivatives with respect to different variables, now we have derivative with respect to one variable. So let's solve this one. Well, this one is easy, right? The second derivative of v with respect to x is 0. Therefore, the derivative of v with respect to x should be a constant, right? And constant here means there is no x in it. So it does not contain x. Now, the good thing here is that we know v does not contain t either, right? Also, there is no t inside v. Therefore, it is really a constant. Therefore, it is a constant. If we were dealing with the same problem in higher dimensions, we would just reduce the number of variables from n to n minus 1. Here we had two variables, we reduced it to one variable, just x. But because the second derivative of v with respect to x is 0, the derivative of v with respect to x is just a constant. So it means that v itself should be, maybe it's better to show it with C1. So derivative of v with respect to x is C1. So v is C1 times x plus another constant, let's say C0. So now we found v. The only things which we don't know about v are these constants, C1 and C0, which of course we can find them using our boundary conditions, right? So v at 0 is equal to C0. It's supposed to be equal to T0. That's our first assumption. Our second assumption, so this is our first assumption. Our second assumption there tells us v at the point A, which is equal to C1A plus C0, which now we know it is equal to T0, is supposed to be equal to T1. We can compute C1 there, right? C1 is equal to T1 minus T0 over A. So now we have the values for C0 and C1. Now, if we plug those into the equation, the solution we have here, we see v is equal to, therefore v is equal to T1 minus T0 over A times x plus T0. We have our steady state solution. So this is not really the solution to the PDE we started with, but it's kind of is the solution in the sense that any solution we have like u of x and t, it depends both on time and the location x. Now, for any solution we have, if we send t to infinity, that function u would converge to this function we found here. Okay. Okay, great. So let's look at one more example of this steady state problem. So our second example would be the same equation. The second derivative of u with respect to x is equal to a constant times derivative of u with respect to t. Our boundary value condition is the other condition we had. So for one point, well, let's say when x is equal to 0, we say u of 0 and t is equal to t naught for any t. For the other side, when x is equal to a, for the other boundary, we use the other boundary value problem. Remember, I said if we have a bar, which at this point a is connected to some air or something, and that means in this, there's air there. That means the equation we have here is something like this, minus a constant. We show that with kappa. The changes in u with respect to x at this point here, a and t, at any time t, is equal to constant times u of a and t minus a constant T1. It's like temperature of air. All right. If you are thinking about it mathematically, it can be anything. It's just given a condition. It's a condition given on, rather than on u at the final point, it's a condition given on derivative of u at that boundary point. It's our other boundary condition. So also suppose we have the initial condition, initial data, which tells us that u of x at time 0 is equal to some given function f of x. And we want to find the steady state solution. So it's quite simple. We should take limit of everything and send t to infinity. So take lim, t goes to infinity from everything. And then what do we get? So again, the first equation, we had that. Partial u partial t goes to 0. The second derivative of u with respect to x goes to second derivative of v with respect to x. So the first equation becomes second derivative of v with respect to x becomes 0. Our boundary values, let's see. The first one, we saw that. It becomes v at the time, sorry, v at the point 0 is equal to t naught. Let's look at the second boundary value condition. Let's see what happens there. So the point is that we have a constant minus kappa, that doesn't matter. We know the derivative of u with respect to x is equal to derivative of v with respect to x. We talked about that. So we saw derivative of u with respect to x. Sorry, it's not equal. What we saw is that at any point x and t, if we take limit of that and send t to infinity, it becomes equal to derivative of v with respect to x at that point, right? It implies here, if you take limit from this equation from both sides, and if we send t to infinity, this derivative there becomes derivative of v with respect to x at that point, which is a. On the right-hand side, when we take limit, well, h is constant. U of a and t would converge to v of a, and t1 is a constant. So our other boundary value condition becomes like this. And as we saw earlier, there is no initial condition. There is no t here, so it gives us no information, no initial condition. Is there any question here? Okay. So now we want to solve this one. Well, it's almost like we did before. So we start with this equation here, just like what we saw earlier. The second derivative of v with respect to x is equal to 0. That implies v is equal to c1x plus c naught, where c1 and c naught, they are constants. Okay. On the other hand, v at the time 0 was equal to t naught. So again, we have C naught is equal to T naught. So now the other thing we want to know is the value of C1. Can we find the value of C1 or not? Let's write down the other boundary value condition we had. We had minus kappa, derivative of V with respect to X at the point A is equal to H, V at the point A minus T1. What can we do here? Does this equation tell us what is the value of C1? Can we find C1 by just looking at this equation? Well, yeah. Well, let's see. So here we have two terms which they contain V. One of them is this one, the other one is this one. So let me rewrite V. So V of X is equal to C1X, which is unknown, plus C naught, which is equal to T naught, right? Therefore, V of A is equal to C1A plus T naught. What is derivative of V with respect to X? Well, if I take derivative from the equation I have there, I can see derivative of V with respect to X is equal to constant C1. Therefore, this other box here is equal to C1. That's great because C1 is what we are looking for. We also have C1 here. Note that we have also C1 here. So if we compute the things, we would see C1 times HA plus kappa is equal to H T1 minus T naught, right? Okay. Therefore, C1 is equal to T1 minus T naught H A plus kappa. Assuming what we have here, assuming this is non-zero, which I think is the correct assumption here. Let's see. So we know A is a positive number. If you remember the definition of kappa, this is a positive number. I think H is also a positive number. Yes. So there's some these constants, if you go back where we defined them, they're all positive. So this is non-zero. We can divide both sides by that. Great. So we have our solution. So V of X is equal to C1, which is equal to H. What was it? I forgot. Oh yeah. H T1 minus T naught. Is it correct? Yeah, I think so. H T1 minus T naught over no, sorry, H was not there. HA plus C times X plus T naught. So this is our steady state solution. Okay. Yeah. Okay, let's see. Great. So we had this equation, we had this partial differential equation. Plus boundary value conditions plus initial conditions or initial condition. And we took limit from this PDE, sorry, and we got an ODE, which was the steady state ODE. And we solved this one. So this was an equation for u, for v. We solved this one and we found the answer. But now the idea is that how we can use this v to go back to solve the PDE which we started with. The point is that we want to solve this PDE. The final goal, which we hope we can do, is solving this PDE. Now the question is that can we use this function which we found here to go back and solve this this PDE? So this is the idea. The idea is that we are looking for a function u of x and t, right? Now this function, as t goes to infinity, becomes more similar and closer, goes closer and closer to v, right? So this function u is almost equal to v, right? It converges to v, so it should get closer and closer to v as t goes to infinity, but it's not exactly equal to. There is some other parts here which depends on time, right? Let's show that with w of x and t, right? So if we take a limit from this equation and send t to infinity, this on the left-hand side, the limit of u with respect to t when t goes to infinity is equal to v of x. V of x itself has no t in it, so it's equal to v of x. And the last term would be limit of this other function, w we defined, where t goes to infinity. Now, of course, these two terms cancel each other, so we can see this function, w of x and t, it goes to 0 when t goes to infinity. So if we take t to infinity, this becomes 0. However, when t is not equal to, it's not going to infinity when t is some smaller number. This is non-zero, but hopefully it's kind of smaller and more manageable. So the idea is, now that we have v, well, if I take w to the other side, I can write w of x and t to be u of x and t minus v of x. Now u was unknown. This was the unknown part. And after solving the steady state equation, this is known. We have v. We know what v is. So the idea is that to substitute w into the equations and get an equation for this other function w and trying to solve that. Okay, and this is usually easier. A lot of times solving the equation for w rather than u is very similar to the things we did before. In a few cases, we did a kind of a trick to go from some non-homogeneous equation to a homogeneous one. It's kind of like that. It makes the equations easier, as we will see. Okay, so the idea is to write down the equations for this new function w. And if we can solve those equations for w, of course, then we know what w is, and then we know what u is, because u is equal to w plus v. So if we find what is the steady state solution, and we can find this other we can solve these other equations for w, of course, their sum would be u, and we're done. We have the solution to our equations. Okay. Now, there are just a few simple computations when we want to go from one equation to the other one. So let's see what are the equations for this other function w. So let's take derivative with respect to x from these equations. Derivative of u with respect to x is equal to derivative of w with respect to x plus derivative of v with respect to x. Right? Now, let's take the second derivative. the second derivative of u with respect to x is equal to second derivative of w with respect to x plus the second derivative of v with respect to x. Now we kind of know what is this term, the second derivative of v with respect to x. Let's go back and look at our steady state equations. These are our equations, right? Remember, the second derivative of v with respect to x is equal to 0, right? When we took limits, derivative of u with respect to t, it goes to 0. So the second derivative of v with respect to x is also equal to 0. So here, this term is equal to 0. And therefore, the second derivative of u with respect to x is equal to second derivative of w with respect to x. Okay, that's great. That's one thing. The other thing is that since, well, u is equal to v plus w, if we can take derivative with respect to t from both sides, derivative of u with respect to t is equal to derivative of v with respect to t plus derivative of w with respect to t, right? Now we know derivative of v with respect to t is 0 because v is independent of time, right? It's the steady state solution. Therefore, derivative of u with respect to t is equal to derivative of w with respect to t. Well, you might think that's not a good thing, right? Because the equation for u was this: the second derivative of u with respect to x is equal to 1 over k derivative of u with respect to t. Now the equation for, what is the equation for this other function w? Well, we saw the second derivative of u with respect to x is equal to second derivative of w with respect to x. So this is equal to second derivative of w with respect to x. And then the second derivative, and then the derivative of u with respect to t. Now we can see here that it is equal to derivative of w with respect to t. And this is a constant. So the equation doesn't change. Why did I say this would be easier? This would be more manageable. Why did we go to solve the equation for w if it's the same as the equation for u? So you're right. The difference is not in the equation. So as you can see, equation for u is the same as equation for w. The thing which makes our life a little easier, they are related to the boundary value conditions. So let's look at, so we don't just have the equation, we also have some boundary value conditions which our function should satisfy, right? One of them was this: u at 0 at any time t should be equal to t naught. Well, we know u at any time at the point 0 by definition is equal to w of 0 and t plus v at that point 0. We also, if you remember, we had boundary value property v of 0 is equal to t naught. We can see that by just taking limits from this first equation and sending t to infinity. If we combine these two, we can see that t naught is equal to w of 0 and t plus t naught. Therefore, the boundary value condition for w is this: w of 0 and t is equal to 0. So it's not equal to some constant. It is a known constant, but it's some constant t naught. It's just equal to 0. Completely in a similar way, we can see that the other boundary condition translates to this one for w. W at the point a and t is also equal to 0. So they are, in some sense, they're better boundary value conditions. They say the value of our functions at the two boundary points, the values are equal, And not only that, but also they're equal to 0. All right, great. We have one more thing. The other thing we have is the initial condition. For W. So we know U at any point X at the time 0 is equal to some given function f of X. Again, I repeat, this function is given. Now, U at any point X is equal to W at that point, and at that time, plus V at that point. Right? That's one thing we know. So if I substitute U of X and 0 with f of X, we see f of X is equal to W of X and 0 plus V X. But the point is that after solving the steady state equation, we know what V is. So after solving the steady state equation, V is known. V is a known function. It's not unknown anymore, right? So, and also f is known, as I said earlier, as I said above, f is given. So if I take V to the other side, both f and V are known functions. So we know what the right-hand side is, right? We know what this thing is. It's not unknown. We know what this thing is. Just name that thing to be another function. Let's call that g of x. So W of X and 0 being equal to g of x would be our initial condition. So we get another initial condition. So the initial condition does not change much. It doesn't get harder or easier. Doesn't change, at least in the general case. But the boundary value conditions, they become better. So equations for U are equal to equations for W. Boundary value conditions for U are harder than boundary value conditions, for W. So we like the boundary value conditions for W better. In general, the initial condition for U is not much different in general. There's no, well, we can't at least compare it to initial condition for W. So in some sense, in general, it's better to start solving these equations with these conditions. So this is what we are trying to do rather than the other set of equations. Okay, now we start, well, if you are following the book, we just talked about the section 2.2, and now we are starting the section 2.3. Now, we start with the case. So the first case we start is that it's just like the last example we had, where the condition, the boundary value condition at the two ends are fixed. They're fixed numbers. So we start with solving this equation. For U of 0 and t is equal to t0, U of a and t is equal to t1, and U x a is equal to, x at the time 0 is equal to f of x. So as you saw, we write this for W, we would get these equations, same equation for W. But W at 0 and t is equal to 0, W at a and t is equal to 0. The initial condition is just something else, another function, where g of x is equal to f of x minus v. Okay, we want to solve this one. So as you remember, I mentioned the first step would be writing down the steady state equation for V and solve that. So that would be this second derivative of V with respect to X is equal to 0. And V at 0 is equal to T naught, and V at A is equal to T1. We solve that, we remember V of X is equal to, well, what was the thing we had? T1 minus T naught, right? T1 minus T naught over A times X. This was the value of C1 in our formulation, plus constant C naught, which we found it's T naught. Okay. Okay, now we know this G is equal to f of x minus vx, which this is our vx. Now we want to find this function w. So I proposed two ways we can solve this one. Let's try both of them. One was assuming that w, the function w, can be written as the sum of two other functions. Let's show them with, I don't know, let's say f1 and f2, where f1 is only a function of x and f2 is only a function of t. This is an assumption, right? This is not something we know it's true. We are just assuming this is an assumption. Let's assume that. Let's see if that assumption helps us or not, right? This is just an assumption. We don't know if this assumption will work or not. But let's see how it would help us, assuming that this function is the sum of two other functions. Okay, so I would again write down our equation up here, so we would have that in front of us. So if w of x and t is equal to f1 of x plus f2 of t, we can take derivative with respect to t from both sides, because here in the equation we have derivative of w with respect to t. I would compute that. Well, it would be derivative of f1 with respect to t, but f1 is not a function of t, so it's constant with respect to t. So its derivative with respect to t is 0 plus derivative of f2 with respect to t. This one is a function of t. We can also take derivative of this equation with respect to x with the star equation. So derivative of w with respect to x is derivative of f1 with respect to x at some point x. Again, f2 is not a function of x, so its derivative with respect to x is a constant. Great. We can take the second derivative. So the second derivative of w with respect to x is equal to second derivative of f1 with respect to x. Now let's plug in these two equations into the equation with which we started with, into, let's say, the triangle equation. So if we plug these things into a triangle equation, we can see that the second derivative of f1 with respect to x is equal to 1 over k times derivative of f2 with respect to t. Now, this is something I explained the other day. This is the key step, so I would explain that again. The point is that here, f1 is a function of x, and therefore its second derivative with respect to x is also a function of x. f2 is a function of t, therefore its derivative with respect to t is also a function of t. It means on the right-hand side, there is no x. On the left-hand side, there is no t. On the left-hand side, we have only x. On the right-hand side, we have only t. And it's not possible for these two things to be equal. One of them should have x in it. The other one is supposed to have t in it. That's not possible. They can't be equal unless both of them are constants. unless there is no x in left-hand side and there is no t on the right-hand side. So the only possibility is that both of them are equal to each other, but actually they are constants. There is no x or any t there. F2 might have t in it, but when we take derivative with respect to t, that t should disappear. F1 is potentially is a function of x, but when we take the second derivative with respect to x, x should disappear. All right, so both of them should be only after taking these derivatives, they should be constants. Okay, so we end up with two equations. So each of them is an ODE. So we started with one PDE, we got two ODEs. So as you can see, that's kind of is the main technique for solving PDEs, kind of finding a way to reduce solving the PDE into several ODEs. That's the idea. So let's solve this one. Let's call this one equation 1. Let's call the other one equation number 2. Let's first solve equation number 1. Second derivative of f with respect to x is equal to this constant c. Therefore, derivative of f with respect to x is equal to c times x. Therefore, f itself, it's a function of x, right? F itself is equal to cx squared over 2 plus another constant. Yeah. Did we have another constant too? Yeah, we could have another constant here. Sorry, I forgot. We would have one extra constant here. So here we would get dx plus a third constant e. So that would be f1, where c, d, and e are constants. Let's look at our second equation. The second equation says 1 over k derivative of f2 with respect to t is equal to constant. Therefore, the derivative of f2 with respect to t at any time t is equal to k times c. So taking antiderivative with respect to t, we can see f2 at the time t is equal to kct plus another constant. What should we use? We have used f, we have used g, we have used h, we have used I for, well, we keep I for a complex number. Let's use j for the other constant here we have. Okay, so that would be the other constant. Now, the function w which we are looking for, we assumed it's the sum of f1 and f2. So it is equal to cx squared over 2 plus dx plus kct plus e plus j. Well, e plus j is just, it's the sum of two constants. It's another constant. We have used k. Let's call this other constant L. Okay. Okay. So what were our assumptions? We said w at, we had some boundary value conditions, right? W at 0 and at any time t is equal to 0. And the other one was w at a at any time t is equal to 0. And now we have w of x and t is equal to f1 plus f2, which is equal to cx squared over 2 plus dx plus kct plus L. Okay, let's plug in these conditions into our equation. Let's apply them to the equation. Let's see what we would get. So what is W of the time 0 and t? Well, if we let x to be 0, the whole first parenthesis would be 0. We would have kct plus L. It is supposed to be 0. This assumption, this condition tells us this is equal to 0. Now we can solve this one. T would be equal to minus L over Kc. We can do that if C is non-zero, right? So we should have an extra assumption, so assume that this constant C is non-zero. Remember where we defined this constant. Here we said because we have a term which is a function of x and a term which is a function of t, and because they're equal, they should be constant. We call that constant C. So first assume that constant is non-zero. We consider the case where C is 0 separately. So if C is non-zero, that would be what we get, and that doesn't make much sense. Do you know why? Can anyone tell me why this thing does not make much sense? This can't be true. Does anyone know why is that? Well, that's in some sense that's correct, but look at this equality we have. On one side we have our parameter t, and on the other side we have a constant. Is that correct? Is it something which is valid or not? Yeah, it is not. So that answer is correct, but we should understand why. So also, would this assume f2 is equal to 0? Well, in some sense, but I want to, let's first understand why this does not make sense. So you can see, look, this t is not something, it's not an unknown to compute. This t is the parameter. T can be anything, right? T is the time variable. It can be 0, it can be 1, it can be 2, it can go to infinity. The right-hand side is fixed. That doesn't make sense. T is not a fixed time to look for, you know? This equation doesn't make sense because on one side we have this parameter t, which can be anything. It's not a constant. It can be 0, 1, 2, 3, 2.5, whatever. That just shows time at the time at different times. Whereas the right-hand side is something which is constant. So the left-hand side is non-constant. Of course, it changes. The right-hand side is constant. They can't be equal. So that's a paradox. That's not possible. So we get to contradiction. So this assumption that C is not 0 gets us to contradiction. So the only thing we can do here is that we should assume C is 0. So let's assume this constant C is equal to 0. Okay. So we have the second derivative of f1 with respect to x is equal to 1 over k derivative of f2 with respect to t equals to a constant. That constant should be 0, apparently. Well, at least the other case does not work. So if we want to assume w can be written as the sum f1 plus f2, c should be 0. This constant should be 0. This gives us again two equations. The equation number 1 is second derivative of f1 with respect to x is equal to 0, and derivative of f2 with respect to t is equal to 0. So let's solve the first equation. Well, that tells us if we take antiderivative with respect to x, that tells us derivative of f1 with respect to x should be another constant. Let's show that with, I don't know, c1, let's say. Therefore, f1 itself should be c1x plus c2. The second equation says derivative of f2 with respect to t is 0, so f2 should be constant. Let's call that c3. Now the function w was the sum of f1 and f2, right? So if we add these two, we would get to the function w. That's what we are going to do. So since w was f1 plus f2, now it would be c1x plus c2 plus the other constant c3. But let's call this constant, let's just give it a name d, right? So w would be c1x plus d. Now let's look at our boundary value conditions. What are the boundary value conditions now? We had two boundary value conditions. One was telling us w at the point x equal to 0 at any time t is equal to 0. And the other one was telling us w at the point a at any time t is equal to 0. Great. Let's plug in these conditions to the equation. So if x is equal to 0, we have the first condition, star. So w would be c1 times 0 plus d, which is just d. And the equation star says this should be equal to 0. Therefore, d is 0. Great. Well, that's up to this point, that tells us w is c1x plus 0. What about the second condition? Well, let's set x to be equal to a. Let's plug in x equal to a to the second equation. To the first equation, sorry, the second condition and first the equation we had. So it would be c1 times a, and this should be also equal to 0. Well, a, we are assuming is non-zero. It's just the length of the thing we had. Therefore, c1 is also 0. Well, great. That just tells us w is equal to 0, which again is not a solution. Well, especially if the initial condition we had g of x, if it's not the trivial function 0, w equal to 0 is not a solution. So again, this does not work. So in this case, this idea of writing w of x and t as the sum of two functions, which one is a function of x and the other one is a function of t, does not work. So what about now? The second step, which is slightly more interesting, is assuming that this function is not sum of two functions, one function of x and the other function of t. It's assuming that, yeah, exactly, it's the multiplication of two functions, one function of x, the other function of t. Again, this is an assumption. We should see if this assumption, if this works or not. We still don't know. We should just assume that. We should try to solve the equation. Either we can get to some solution or prove there is a solution, or again, we get to some sort of maybe contradiction and we would say this does not work. So we should try to see that. And hopefully, so the idea here, trying to break the solution into different parts, which each part is a function of just one variable. In one case, writing it as the sum of two things, and in the other cases, their product, is that using these techniques, we hope to reduce the PDE into several ODEs, which we know how to solve them. So that's the idea. Okay. Okay, let's continue. So as I mentioned, our idea to solve this one, the method is to assume that the solution to this differential equation can be written as product of two functions, one just a function of x, the other one is a function of only t. So this is called the product method. We are solving this equation. And we are assuming that the function w of x and t can be written as a function of x times a function of t. As we know, where our boundary assumptions, the boundary conditions are, both of them are 0. Okay. Okay, let's start. So here in our equation, we have derivative of w with respect to t. So we are going to compute that. As we know, f1 is just a function of x, there is no t. So when we are taking derivative with respect to t, we regard f1 as a constant. So it would be f1 of x, derivative of f2 with respect to t. The other term we have here is the second derivative of w with respect to x. So we are going to take the second derivative with respect to x. Again, here, f2 is like a constant. So we would have f2 of t times the second derivative of f1 with respect to x. Now, if we plug in these things we have into the equation, let's show that with star. If we plug these into the star, we are going to get this thing. So f2 of t times the second derivative of f1 with respect to x is equal to 1 over k derivative of w with respect to t, which is f1 of x derivative of f2 with respect to t. Now, note that there are terms which they only have x, and there are terms which they only have t. So some terms like this one and this one, they only contain t. Some terms like this one and this one, they only contain x, right? So the idea is to separate variables. That's what we are going to do. So I would move everything with x to, say, left-hand side and everything with t to right-hand side of the equation. So we are going to divide everything actually by f1 times f2. If we do that, this would be the result. The second derivative of f1 with respect to x, which is a function of x, over f1 of x, yeah, of course, equals to derivative of f2 with respect to t at some point t over f2t. There should be k here too. We would get this equation. Divide everything by f1 and f2. Yeah, that's correct. So again, we would have the same argument as before. The left-hand side is only, it's just a function of x. No t. The right-hand side is a function of t. No x. They can't be equal unless they're equal to a constant, c. Now, there are different cases. We should consider each case separately. So let's do that. There are different cases. One case is that C is 0. One case is C is not 0, but actually we should consider it more carefully. So say case number 1 is where C is positive. Case number 2 is when C is 0. Case number 3 is when C is negative. Okay. Great. Let's start with the first case. So the equation we have is this one. Which is positive. And derivative of f2 over derivative of t over k. f2 is also constant. Right. Let's show one equation with star, the other equation with double star. Okay. So the first equation tells us the second derivative of f1 with respect to x minus c times f1 is equal to 0. And the second equation tells us the derivative of f2 with respect to t minus k c f2, which is also a function of t, this is also equal to 0. These are the two equations we have, right? Okay, let's start to solve the first one. This is a second-degree linear homogeneous equation. So we have a homogeneous equation. We would look at the characteristic polynomial in this case. What is that? So in this case, it would be m squared minus c equals 0, right? M squared minus c is equal to 0. Therefore, m squared is equal to c. Therefore, m is equal to plus and minus c. So in this case, we know what the solutions are. m1, let's say m1 is equal to c, m2 is equal to minus c. We have two real solutions, right? So what are the solutions? We have y1. Let's show this one with y1 to be, or maybe let's just write down let's just write it as f1. It's equal to a constant times e to the cx, where this c1 is just a constant and the c appearing here is the same c as we had in our equation, plus c2 times e to the minus cx. Okay, that would be our f1, right? Now, there are also boundary value conditions. So let me write down the boundary value conditions. So f1 of x is equal to c1 e to the cx plus c2 e to the minus cx. And the boundary value condition is this thing. So we had w of 0 and t should be equal to 0, and w of a and t should be equal to 0. So because w is equal to f1 times f2, it means f1 at 0 times f2 at t should be equal to 0, and the other condition would be f1 at a times f2 at t should be equal to 0. Okay. So you see, the product of two things is equal to 0. So either f1 of 0 is equal to 0, or if that's not equal to 0, f2 of t should be always 0. So one case is to say f1 of 0 is equal to 0, or f2 of t is 0 for any t. But the problem with the second thing, this one, is that If f2 is always 0 for any t, and if w is equal to f1, f2, then w would always be 0. And that's not an interesting solution. It probably wouldn't satisfy the initial condition. Even if it does, even if the initial condition is w being 0, this is a trivial solution. So w being equal to 0 is not interesting to us. This is not our answer. Therefore, we should assume f1 of 0 is equal to 0. Okay. What does that tell us? What is f1 of 0? Let's use this definition we have here to see what is f1 of 0. It would be c1 times e to the 0, which is 1, plus c2 times e to the 0, which is 1. So c1 plus c2. But this condition here, it says it should be 0. So c1 plus c2 is equal to 0. So c2 is just minus c1. That's one relation we have here. Right? Now, but there is another boundary condition, which is this other one. Let's look at that. That one says f1 at a, which is equal to c1 e to the ca, plus c2, which c2 is just minus c1 e to the minus ca, times f2t should be equal to 0. Just like the previous case, either this one should be 0 or the other one, but because we don't want f2 to be 0, because if that's 0, w is 0, this also implies that f1 of a is equal to 0. Therefore, this thing we have here, which is f1 of a, I just plugged a into the definition of f1, this should be 0. Now I can divide everything by c. So divide by, sorry, we can divide everything by c1. So e to the ca minus e to the minus ca is equal to 0. What does that tell us? So let's look at this equation. E to the ca minus e to the minus ca is equal to 0. That means e to the ca is equal to e to the minus ca. If we divide everything by e to the minus ca, we get e to the ca over e to the minus ca is equal to 1. Therefore, e to the ca plus ca, which is 2ca, is equal to 1. That means, well, if you take log or ln from both sides, that means e to the ca, if it's 1, the power should be 0. So 2ca should be equal to 0. But first of all, a is non-zero. A was the length of the bar we had. So I can divide everything by 2a. It implies c should be 0. And that is a contradiction. Why is that? Well, remember, we are in case number 1, right? We had 3 cases, case number 1, 2, 3. We are in case number 1. We already have assumed c is positive. But if we assume c is positive, it's if we follow the equations, we conclude c is 0. That's the contradiction. Therefore, the first case does not work. The first case can't be the answer. C can't be positive. Okay, let's look at the second case now. Let's focus on the case where c is equal to 0. So this c here, this constant here is equal to 0. Therefore, this guy here is 0. Also, this other term here is equal to 0. So the second derivative of f1 with respect to x over f1 is equal to 0. That's one function. That's one condition. The other condition is derivative of f2 with respect to t over k f2 is equal to 0. Well, the first one simply means the second derivative of f1 with respect to x is equal to 0. The second one simply means derivative of f2 with respect to t is equal to 0. If we solve the first one, it means derivative of f1 with respect to x is a constant. I would show that constant with c1. If we take antiderivative with respect to x, it tells us f1 is c1x plus another constant, let's say c2. If we take antiderivative from the second equation, the equation which is written with respect to t, we would get f2 is another constant, say c3, right? Now w was f1 equal to f1, f2, which would be equal to c1x plus c2 times this constant c3. So it's equal to c1, c3x plus c2, c3. I would call this part d1, it's just another constant. I would call this part d2, it's just another constant. So w would be equal to d1x plus d2. And note that there is no t. Okay. Let's see if it satisfies the boundary value conditions. So w of x and t here is independent of this. d1, a constant times x, plus d2, another constant. What is our boundary value condition? Well, we have two conditions. One tells us w at 0 at t equals 0. The other one tells us w at a and t is equal to 0. Okay. Let's plug in x equals to t into our equation. So if x is equal to 0. So if x is equal to 0, w of 0 and t would be equal to d1 times 0 plus d2, which is just d2. And this condition star here tells us w of 0 and t should be equal to 0. So that is equal to 0. Therefore, d2 is equal to, well, d2 is equal to 0. So here, there is no d2. It is just 0. What about the other condition? Star, star. In star, star, x is equal to a. So let x to be equal to a. Let's plug that into the equation. W of a and t should be equal to 0. But what is that? Well, that is just d1 times a. That should be equal to 0. Well, we know a is not equal to 0. A is non-zero. A is the length of our rod. So that is non-zero. We have some non-zero thing. Therefore, d1 is equal to 0. If d1 is equal to 0 and d2 is equal to 0, w is equal to 0 at any place and at any time. And again, that's not the solution we are looking for. So that also doesn't work. So if we go back to the cases we had, c being equal to 0 also does not work. So the only remaining case is the case where c is negative. So the only remaining case is where these two are equal to a constant which is negative. Is there any question up to this point from the things we discussed before starting the negative case, the case number 3? Okay, let's continue with the last case. Hopefully it would work. If it doesn't work, we are kind of doomed. Our idea didn't work. We can't, at this point, we can't do anything, right? But actually it's going to work. So let's consider the third case. So the third case tells us that it gives us two equations. The first one, the second derivative of f1 with respect to x over f1 is this constant c, which we are assuming it is negative. and derivative of f2 with respect to t over kf2 is this constant, which again, we are assuming it is negative. So we get two equations. One equation is this one. And the other equation is this one. Okay. Okay. So let's start with equation star, the first one. This is homogeneous, so we write down the characteristic polynomial. We would have m squared minus c equals 0. Now here, note that c is negative. So minus c is something positive. M squared plus something positive is equal to 0. The solutions are going to be complex. They're not going to be real, right? So m squared is equal to c, where c is negative. Therefore, m should be plus minus I squared root of minus c. Okay. So for example, c is something like -1, then the solutions would be plus minus I. Maybe for notation, what the book has done is better. What the book has done is this. Book says c is negative, right? So minus c is positive. Okay. So if it's positive, so minus is positive. If it's positive, it's the square root of that is a real number. Let's call that lambda. Therefore, minus c is lambda squared. So c is minus lambda squared for some lambda. So if rather than using c, we can use this lambda. So the equation m squared minus c equals 0, it becomes m squared plus lambda squared equals 0, right? So m squared is minus lambda squared. Therefore, m is plus minus I lambda. So let's say m1 is I lambda and m2 is minus I lambda. So, in the case where our solutions are complex, here only imaginary, the solutions to the homogeneous equation are of the form cosine lambda x and sine, well, here minus I lambda, it becomes sine of lambda x. So the solution, which we named that f1 of x, would be a linear combination of these two. That would be the solution. That would be the solution to the equation star. Remember, this is the equation star. So we have the solution to this equation. Okay, now let's start solving the second equation, star star. So the second equation was this one, the derivative of f2 with respect to t minus k c f2 equals 0. right? So we have solved this. These are we have seen these first order equations. So the second derivative, so the derivative of f2 with respect to t equals kcf2 of t, right? So we can do the separation of variables. I would just write down kf2 just for simplicity. So df2 over f2 would be equal to kc dt. I would show partial t with d because actually it's just function of one variable, and you are more familiar with this for. Now we can integrate both sides. We would have df2 f2 equals integral of kc dt. Is there any question up to this point? Everything's good? Great. So the left-hand side, the integral of df2 over f2 is equal to ln of absolute value of f2 plus constant, and integral of kc dt is equal to kct plus another constant. Therefore, we would have ln of absolute value of f2 equals kct plus constant. It means absolute value of f2 is a constant times e to the kct. We can drop the absolute value. There would be just some plus minus, which I would absorb it to constant. So it would be a constant times e to the kct. Let's show that constant with, say, a. Okay. Now, w was the product of these two things, right? So let's see. W of x and t was equal to f1x times f2t, right? So what was f1x? Let's recall we computed f1, right? We had f1 right here, c1 cosine lambda x plus c2 sine lambda x. That's f1. Okay, there is a question. We don't have c equal to 0. So you're saying if c is negative, why do we have c is equal to 0? Yeah.
So what I'm saying is like, can you go back to the slide where you have the two equations, like df2 and
Not this one. Yeah. Let me.
For the case where c is
This
less
one.
than 0. Yeah. So my question is, if c is less than 0, that's automatically already a negative. But when you wrote it, you put when you moved it to one side, you put a negative. So
yeah. So
would that make the exponent in the second one, would that make it a negative exponent or positive?
okay, c is negative. That is correct. So you are talking about something in this slide?
Mm-hmm.
Okay, so c is still negative. We have c here, which is negative. Here, absolute value of f is equal to a constant times e to the kc. This is still negative. And then when we drop absolute value, we would get a plus minus here, which I would absorb into this constant. But the c here is still negative. Is that what you're asking?
Yeah, okay. Okay.
Yeah. Yeah, this is true. See, this is a negative number here. That's correct, yeah. Okay, and then we know W is F1 times F2, where F1 is C1 cosine of lambda x plus C2 sine of lambda x times F2 of t, which is some constant a e to the k ct. Now there are two things. One is that when I multiply, I can multiply a by this parenthesis, and a is a constant. This c1, c2 are constants. I can just combine them to get, say, d1 cosine of lambda x plus d2 sine of lambda x. On the other hand, here I have a kct, as you mentioned, because c was negative, we could write c as minus lambda squared, right? Because c was negative, its negative would be a positive number, which I can write as lambda squared. So if I plug that in here, I would get minus lambda squared kt. So this would be the solution. There are still unknowns here, d1 and d2. We don't know what these values are. Now we can look at the boundary value conditions. So let's look at our boundary value conditions. So one was telling us w of 0 t is equal to 0. The other one was telling us w of a and t is equal to 0. Great. Let x to be equal to 0. Plug that inside this equation. We get d1 cosine of 0. Cosine of 0 is 1, so d1 plus d2 sine of 0, which is 0, times e to the minus lambda squared kt should be equal to 0. Well, e to any number, this exponential, is non-zero. So if this product is 0, if the second term is non-zero, d1 has to be 0. Great. So d1 is 0. So this term disappears, d1 cosine of lambda x, because d1 is 0. Let's look at the second condition. Let's let x to be equal to a. There is no d1 anymore, so d2 sine of lambda a times e to the minus lambda squared kt should be equal to 0. That's what our second boundary condition tells us. Again, we know this exponential term, e to anything, is non-zero. So the term which we have here should be equal to 0. Okay. Therefore, d2 sine of lambda a should be equal to 0. Is there any question here? Okay. If not, let's continue. Okay, so the boundary conditions for W, they become some conditions for D1 and D2. One of them simply says D1 is equal to 0. The other one says D2 sine of lambda A is equal to 0, right? Now D1 being 0, that's clear. The second condition, we have multiplication of two things being 0. There are two things that might happen. Either d2 is equal to 0 or sine of lambda a is equal to 0. Okay, if d2 is equal to 0, that's very, very bad, right? Because remember, what was f1? f1 was d1 cosine lambda x plus d2 sine lambda x. If d2 is 0, since d1 we also know that's also equal to 0. The whole f1 would be 0. And if f1 is 0, w, which was equal to f1, f2 would be 0. So w is just 0. And this is not the solution we are looking for. W being 0 is not the interesting solution. So this is not something we are interested in. We don't want D2 to be 0. So we are just left with one case. Sine of lambda A should be 0. Okay, but we know what are the angles where the sine is 0 there, right? If sine of something is 0, that means that angle is equal to an integer times pi. So it should be equal to an integer times pi. So it can be something like 0 plus minus pi plus minus 2 pi plus minus 3 pi, etc. Right? So in general, I would just show it with n pi, where n is an integer. It's something in z. So the final result here is that lambda A is equal to an integer times pi, and d1 is equal to 0. And we didn't find any condition on d2. One condition was telling us d2 is equal to 0. We did not accept that condition. At this point, there is no condition on D2. Okay. Now, the funny thing is that for any integer n we choose, we would get one solution. So for any integer n, we get one solution. How is that? So suppose n is fixed. Suppose n is 1, 3, 17, anything. Then lambda A being equal to n pi, what does it tell us? Well, lambda was a constant. We know how it's related to c, right? That's something which we already know. From this equation, what we get is that maybe it's better to call this lambda sub n to mention this is a function of n. From this equation, we get lambda n is equal to n pi over a. A was also the length of our rod. Okay, so for any n, if we let lambda n to be n pi over a, we would actually get a solution, because then it tells us that f1 of x, which was d1 cosine plus d2 sine, well, d1 was 0, so it's just d2 sine of lambda x will become equal to n pi over a x for any d2. So for any d2, we have this f1, right? And f2, which was a function of t, was also equal to a constant. I wouldn't write down the constant here, e to the minus lambda squared kt, which again here it becomes equal to e to the minus lambda squared is n squared pi squared over a squared kt. So for any n, the product of these two is a solution to our equation. Okay, so for any n, w being equal to a constant, which we still show that with d2, times sine of n pi over ax, times e to the minus n squared pi squared over a squared kt is a solution for every n. So we have infinitely many solutions for n equal to 1, n equal to 2, n equal to 3, etc. Now there's one small point here. Okay, let's go to the next page. If we choose lambda being equal to n pi over, what was it? N pi over a. If you change n to minus n, we wouldn't get a new solution. So I'm telling you, for every n, we have one solution. So for n equal to 2, we have a solution. For n equals to 3, we have another solution. And they are independent solutions. But if you change n to minus n, we don't get a new linearly independent solution. Why is that? Well, remember, our solution is of this form: a constant times cosine of lambda x, sorry, sine of lambda, which is n pi over ax, e to the minus n squared pi squared over a squared kt. Now, if we change n to minus n, that is another solution, but that doesn't change anything here, right? We're squaring that thing. So n squared is equal to minus n squared. We would get a minus sign here in sine, but you know sine of minus alpha is equal to minus sine of alpha. So this sign comes out. So I can erase this sign from here. I can write it here. But minus a constant is another constant. So that's not anything new. So that shows us that we have independent solutions for just maybe looking at positive or non-negative numbers. Actually, positive numbers. If it's 0, it would be trivial solution. So for n equals to 1, 2, 3, etc., for each n, we would have one solution, one linearly independent solution. So the general solution coming out of this technique would be this thing, a linear combination of these things. So a constant, let's say C1 times sine of, well, let's take n to be equal to 1. So it would be sine of pi over ax e to the minus pi squared a squared kt plus C2. Now let n to be equal to 2, sine of 2 pi over ax e to the whatever plus n to be equal to 3. We get infinitely many solutions. Any finite linear combination of these things for any numbers n would give us another solution. Okay, so now we have a lot of solutions for w. Remember, we computed the steady state case. Well, before going there, let me just remind you something. So the functions we found now, they satisfy the equation. So all of them, they satisfy this equation. Great, that's just great. All of them satisfy the boundary value condition too. That's how we found what are these lambda and the constants. There is one thing left, and that's the initial condition. Initial condition tells us that w, remember, at the time 0 at any point x should be equal to some given function, which it was actually f of x minus vx. Because we can compute v and f is given, if it's subtracted, it would be another function. Let's just we called that just gx. So w of x and 0 should be equal to gx. Now, let's focus on this initial condition. Let's see what does this equality tell us about the solutions we found. So w of x and t is equal to sigma, some constant, Cn, sine of lambda n, which is equal to n pi over ax, e to the minus n squared pi squared over a squared. This is lambda squared kt. Any linear combination of these things is a solution, right? On the other hand, the initial condition tells us w of x and 0 should be equal to this function gx, which is equal to fx minus vx. So let's plug in this condition into the equation. Let t to be equal to 0. If we let t to be equal to 0, we get w of x and 0. So let this t here be 0. We would have e to the 0. E to the 0 is equal to 1. So we get sigma cn sine of n pi over ax. Now this is supposed to be, the condition says it's supposed to be fx minus vx. Okay. Now I want to find cn. So the goal is to find, I want to find cn, all these coefficients cn. I want to know what are these coefficients. How can I do that? So this is the idea. Integrate both sides of the equation. Integrate both sides of this equation with respect to x. There's just one variable here. So integral of sigma cn sine of n pi over ax dx is equal to integral of fx minus vx dx. Okay, we are just integrating both sides, right? Now, the bounds for integral, well, x is defined from, remember, x is on our rod, x starts from 0 goes to a. So let's take integral from 0 to a. Remember, if we had some assumptions on the type of convergence, like uniform convergence, we could interchange the places of summation, infinite summation, and integral. I'm going to do that assumption. So here on the left-hand side, you would have sigma, and goes from 1 to infinity, integral from 0 to a. And cn is a constant, so it comes out of integral. So cn times sine of n pi ax dx. Okay, it should be equal to integral from 0 to a fx minus vx dx. Suppose we can compute this integral on the right-hand side, right? Fx is given, we can find Vx, subtract them, take the integral. Suppose we can compute this integral. So I'm assuming we have, this is something we can compute. This is something which is okay. We can compute that. Let's call this number whatever it is, let's call this number I. This is a number which we can compute. Okay, there's just one step. Is there any question? We would finish in a few seconds. Is there any question before ending today's meeting? No?
Yeah, I have a question. For the sum that you have written for W, you're saying that as a general solution, it can be an infinite sum?
Yeah, just like the Fourier series we had before.
I guess my question is, you know, we should, I guess there's a limit there though too, right? Like don't you, like you can say that this sum of two solutions is a solution.
Yeah, but if you have infinitely many solutions, if the sum converges in a good sense, for example, uniformly, the infinite sum, the infinite linear combination is still a solution, still a valid solution.
So my question is, if we've already assumed that you can write an infinite sum and have that sum be a solution, then does that give us the ability to pull this integral inside?
Yeah,
Or-
kind
or
of.
the-
It is a little still tricky, but at least in the cases we discussed, yes. In more
Okay.
general sense, no. There are sometimes, you see, we are assuming this sum is a function. Sometimes solutions satisfy some equation in a weaker sense. They are called weak solutions to a differential equation, And in those cases, we still think about them as a solution, but we can't do this thing. This is not something you would see in this course. They're related to something called sublove spaces or weighted sublove spaces. So in this course, yeah, but the answer to your question is no in general. Sometimes we accept even weak solutions, but if you want to think W is a function, well-defined function, yeah, then we can interchange these two. Okay, I would finish in just a few. Yeah, sure. I would just finish in a few seconds. So one other thing we can do here is that we can multiply everything by sign. So look at this equation here. Right? Suppose I want to compute say Cm for some m. I'm not saying n because n is the index summation. Suppose I want to compute some Cm. Multiply everything by sine of n pi over m pi over a. So in that case, we would get sigma Cn sine of n pi over a sine of m pi over a, and goes from 1 to infinity, equals to fx minus vx sine of m pi over a. We integrate both sides. Now, the point is that this integral is 0, as we have seen before, unless n is equal to m. So on the left-hand side, in the summation in the left-hand side, all terms are 0. Just one term is non-zero. And that's when n is equal to m. And in that very specific case, the integral is equal to a over 2. So we have Cm times a over 2. This is the term when n and m are equal, plus every other integral is equal to 0. On the right-hand side, we have this integral from 0 to a. I'm taking integral from 0 to a. Fx minus vx sine of m pi over a x dx. Sorry, both of these things have x in it. I just forgot the variable. Well, that tells us Cm, the thing we were looking for any m. For any m, 1, 2, 3, etc., Cm is equal to 2 over a, integral from 0 to a, fx minus vx, sine of m pi x over a dx. From this equation, assuming we can compute these integrals, assuming you're able to compute these integrals, these equations gives us all numbers Cm. And when we have these numbers Cm, we have W, right? What was W? So remember, W was W of x and t was equal to sigma Cn times sine of n pi over ax, right? Now we have these numbers for W, for Cn. They are equal to 2 over a, integral from 0 to a, times fx minus Vx times, n goes from 1 to infinity, times sine of n pi, sine of, maybe I should write it here, sine of n pi over ax dx. This was the coefficient, the whole integral, times sine of n pi over ax. And then we have this summation. This is w. And if we add to this w, if we add to w the v, which was the steady state solution, their sum would be u, and u is the solution to the original PDE we started with. Okay, here I stop. You can ask any question you have, but here I stop the class.